One of the classic mistakes people make when they discuss polling and sampling is they often think that the sample size isn't large enough. And I'm here to show you that that's not so. So, for example, when CNN or Gallup or news organizations in general poll people, they often poll around 1,000 people, more or less. And a lot of people get all upset about this if they don't know anything about statistics, and they say, oh, that's not enough people. There's 300 million people in the US. How is 1,000 people good enough? And the answer is 1,000 people totally could be good enough. Let me explain to you why. If you go to the doctor when you're sick and they have to draw blood to kind of run some tests, do they have to draw all the blood in your entire body to figure out what's wrong with you? Well, I should hope not, because you are going to a vampire doctor, and that would not be good. No, you don't need to have all the blood in your body drawn to figure out what's wrong with you. You only need a few vials, as long as they're well drawn, right? So, no, do not need to draw all the blood. You only need a couple well-drawn vials of blood. Of course, those vials must be samples, must be random, unbiased, etc. Right? We always have to have random and unbiased, otherwise we're in big trouble. If that's the case and you have a random unbiased sample, how big do you need? Well, it depends on what you're interested in. So we have these two formulas here. These are for sample size when you're trying to estimate a single population proportion. I want to know what proportion of people are going to vote for so-and-so. I want to know what proportion of people are going to give away Halloween candy this year. I want to know what proportion of people want to make abortion illegal. I want to know, et cetera, et cetera, et cetera. So how many people do you need to poll? Well, there are two options. You either have a prior estimate. That means you've done some study before. You did a poll on this election last week, or you did a poll on abortion last month, or you did, a poll about candy last year, that kind of thing. Or you have no prior estimate. You've never done a poll on this. You just have no idea where it is. So those are your two options. Now, both of these formulas are on your inferential statistics info sheet. They're down here with the sample size formulas. They're these two right here. So if you're going to do a single sample proportion with a prior estimate, that's this one on the left. And with no prior estimate, that's this one on the right. So remember, you don't have to even put the formulas on your note sheet. They are given to you right on that inferential statistics sheet on the front page. Now notice both of these formulas must be rounded up. You have to round up. You can't pull 0.3 of a person. And you have to round it up because if you go any lower, you won't have the margin of error or the confidence level you were looking for. And the margin of error for these ones is a decimal always, because this is for proportions. It will always be a decimal value. All right, so suppose we want to know how many students we need to poll to find out whether statistics professors at JCC are awesome. So we want to go do a poll of JCC math professors, because just how we are, and we need to know how many people do we need to get? How many students are we interested in? So we want 95% confidence with a 4% margin of error. Okay, so here's the formula for it because we have no prior estimate anywhere in here. It didn't tell me that I've done this poll before or anything like that. All right, so then I know it's 0.25. Now let's see, the error comes from the within part right here, within a 4% margin of error. See that right there? So because of that, I know that the error is 0.04. Right? So I'm going to put 0.04 in that denominator. 0.04 must be a decimal because you're dealing with proportions here. So everything's got to be a decimal. Now I just need my z. Well, my z alpha over 2 comes from my confidence level. So my confidence level was 95%, which means z alpha over 2 is 1.960. We found that, back several pages in section 9.1, right here, 1.960 right there. That's the one that goes for a 95% confidence level, right there. All right, so I know that's 1.96, so I'll use that number and put that up here, 1.96. Now I just have to find this with my calculator. So let me grab the calculator. 0.25 parentheses 960 divided by 0.04, close your parentheses, squared is right over here with that little x squared button. And then I press enter, and I get 600.25. So this is 600.25, and therefore I need to poll at least 601 people. You have to round up, no matter what. No going down to 600. All right, wonderful. Made a little note to ourselves. Remember, must round up. And this one we found in table previously, right? We found that already, that value 1.96 already on a previous problem or previous page. All right, so now what if we do it again with 95% confidence, but this time I want a 3% margin of error. So I'm trying to make it so that my interval is more accurate, okay? Well, all of this stuff is still the same except the error. The error is now 0.03. So in here, I'm going to change this number to 0.03. So let's see what that does. So I say 0.25 times 1.96 divided by 0.03, close your parentheses, squared, enter. And I get, holy camole, 1067.111. So this is 1067.1 repeating, and that would be 1068. And there we have it. All right, now what are we noticing here? How do these two problems relate to each other? They stayed the same confidence level, but the margin of error went down to a 3% from a 4%. And when that happened, the number of my sample, the size of my sample, increased, right? It went up, increased. Right? That makes a certain amount of sense. Error is in the denominator, if you look at it. So error is in the denominator. So if it goes down, the overall number will go up. They're inversely relational to each other. When error goes down, n goes up. There, and I just typed that up into a little comment right here, that there's an inverse relation between error and sample size. That is, if error goes down, sample size n goes up, and vice versa. If n goes down, n goes down, then error goes up. All right, now what if I leave my 3% margin of error this time? So I'm leaving my error alone, but now I'm increasing my confidence level. So I'm changing it from a 95% to a 99%. Okay, so error is now 0.03, but what's that going to do to my n value? N was 1.96 when I was dealing with 95%. Let's go back and look at what it is for, there it is, 99%. That's this one right over here, this kind of, it's off on the edge. Oops. There we have it right there. So I'm going to make it a little bit lighter. I'll make it kind of this very light gray so you can see it. Right, so there it is. And then you can see that the number increases from 1.96 to 2.576. So it's going to increase my z value. So let me go back down. Oop, not that far. There we have it. Okay, so I'm going to increase my 1.96 to 2.576. All right, now what's that going to do? 2.576 is in the numerator. So if you make it larger, since it's in the numerator, it should make the overall number larger. Let's see if that's true. Let me grab the calculator. There it is. So I'm going to say 0.25 times 2.576 divided by 0.03, close your parentheses, squared. And sure enough, I was right. It's 1843.27. 1843.27, which would round to 1844. So you need considerably more to have that large a confidence with that small an error. All right, so then we're seeing that there's a direct relationship between confidence level and sample size. So if your confidence level goes down, right, it's confidence level, well, actually in this case goes up, sample size goes up, or n goes up, and vice versa. If they go down, they both go down, right? Actually, I put up here the increasing right here, so I'm going to put increases right here. That's the one I just said. If one goes up, the other goes up. And I'll say this one, if it goes down, if your confidence level goes down, then the n goes down, n being your sample size. Right? And this right here is little n right there. So this one has an inverse, error has an inverse relation because error is in the denominator. So that makes it an inverse relation. When error goes up, sample size goes down and vice versa. Okay. As a matter of fact, let me change this because I wrote error goes up, n goes down, and vice versa. And the vice versa is what I wrote right here. Error goes down, decreases, then sample size goes up. For the confidence level, because it's in the numerator, your z alpha over 2 is in the numerator. When confidence level goes up, increases, sample size goes up. That's direct relation. And by the same token, if confidence level goes down, n goes down. They go together. Up and up, down and down. All right, now what if we had a prior estimate? What if we have some known old study, like last year, they did a study of what students think of JC stats professors. They found that 67% of students think that they're awesome. Okay, well, that's a different formula. Because I have the prior estimate, n equals p hat times 1 minus p hat over n, times 1 minus p hat. And then the z part is still the same. Z alpha over 2 over the error squared. Okay, so the p hat is our prior estimate, this one. And we know that the p hat is from the old study, is 0.67 from old study, old survey. And then I still have error is 3%, so 0.03, and I still have 99% confidence. See it right here? 99% confidence, 3% margin of error. There's that one, and then 67%. That's the old study. All right, so I highlighted those key pieces of info. Remember that the error is still 0.03 and the z is still 2.576 because it's a 95 or 99% confidence level. So I have 0.67 times 1 minus 0.67. Then I have my fraction, which is 2.576 over my 0.03 error. I'm going to square it. So let me grab the calculator. 0.67 parentheses, 1 minus 0.67, close that parentheses. Then open a new parentheses for the 2.576 divided by 0.03, and then I want to square that last part. And I get 1630.19, 1630. It's getting a little long here. 1630.2, which would be 1631. As our final result, as always, we have to round these up. We must. Now you'll notice that this had the same error rate and 99% confidence level as the last one, which was 1844. But you don't need as big an amount of sample if you have a prior estimate. That is, you don't need as big a sample if you have an old study or survey to draw some info from.